The paper which will be presented is Location-Aided MmWave Hybrid Precoding Prediction for Air-to-Air Communications. I divided my presentation into these 5 parts. First, I will introduce some background and some recent research results about mmWave massive MMO hybrid precoding and mobility systems. Dramatic growing demand for high data rates services such as remote sensing, disaster warning, and so on have promoted the air-to-air communication attract much attention. However, the air-to-air communications often need long-range data transmission and accompanied by the high relative velocity between the transceiver, which results in a poor communication quality due to the significant path loss and high mobility. Fortunately, mmWave and massive MMO have recently been demonstrated as some useful means for high data rate communications. On the one hand, mmWave offers huge available spectrum bandwidth. It has been envisioned as a key technology to provide high data rates in future air-to-air systems. On the other hand, small wavelengths of mmWave signal make it possible to pack large-scale antenna array into an air with limited size to provide huge array gain. However, due to the high cost and power consumptions, the conventional full digital architecture is unaffordable in practice, so the hybrid precoding was proposed. The number of RF chains is fewer than antennas, but it then can achieve performance close to the full digital architecture. However, mmWave is rarely employed in long-distance outdoor communications because of its severe free space attenuation and absorption loss. Nevertheless, the dimension influence of the unload signal at altitude increase. Therefore, with a large-scale antenna array, highly directional beamforming can compensate huge path loss of those channel at mmWave. Meanwhile, for the high mobility system, most of the researchers take MMO for digital architecture into consideration. On the one hand, to achieve the optimal spectrum efficiency, perfect channel state information is needed, where it is quite challenging to be obtained in practice. On the other hand, the directional beamforming is rarely considered and resulting in a short channel coherence time under high mobility scenarios. In addition, due to the high complexity and power consumption of for digital architecture, it is unaffordable for air-to-air systems. To overcome the above problem, we use a hybrid precoding architecture. It can perform both low-dimensional digital precoder, digital signal processing, and directional beamforming. Unfortunately, most of the existing studies assume the relative velocity between the transmitter and receiver is low, and the range of communication is short, which may not hold in air-to-air systems. So we propose a novel two-stage hybrid precoding strategy. Next, I will talk about the system model and channel model. There is a control center communicated with multi-mobile nodes. They both fly at high altitude, and the relative velocity between them is also high. This picture, figure 1, is a more concrete representation. The control center and mobile node are both equipped with uniform planetary array. For the control center, we assume a full connected architecture, while for the mobile node, only analog beamforming is considered due to the energy constraints. This page mainly describes the specific expression formula of hybrid precoding and the objective function of the system in Formula 3. Then we talk about the channel model. The channel of kth mobile node for mth time slot is presented, and Doppler shifter is also presented here. Due to the equipment of uniform planetary array, the steering vector is a conical product of the horizontal plane and the vertical plane. Next, we consider the channel for two adjacent time slots according to the channel correlation coefficient. For omnidirectional antennas, the correlation coefficient obeys Jake's model, but for directional beamforming, it can be expressed as in Formula 13. Then we will have the evolution channel model in 11. In addition, for array steering vector for the next time slot, we can use Taylor expression to express. For long-distance air-to-air wireless communications, in a short time, the variation of angle of arrival and departure are small. The effect of the angle variations on array steering vector assumed to be neglected. Finally, the evaluation of channel can be written in Formula 17. Next, I will discuss the hybrid precoding processing under the fast time variant channel. The proposed strategy leverages the channel correlation to maximize the spectrum efficiency. We reduce the complexity. As you can see from the picture on the hand side, when we know the location information of mobile node, for example, vector QK, it is easy to get the angle information due to the loss channel in air-to-air system. We can utilize the geometrical relationship between location information and angle information to calculate the AOA and AOD. It is assumed that the phase-only controlled phase shifter is employed, and we match analog precoder and combine with array steering vector and array response vector, respectively. For the given direction, the ideal analog precoder and combine of the KTH mobile node are formulated in 18. Then we define the beam update period TB as the location information update time, and NTH BOP, location and relative velocity for the KTH user is defined in Formula 19. It is assumed that the mobile node is moving uniformly and in a straight line during one beam update period. The location information of n+1 th beam update period can be written in Formula 20. Moreover, AOA and AOD of n+1 beam update period are obtained depending on Formula 17. Next, I will talk about the design of digital precoder. Since the mobile nodes are not separately, there exists interference among data streams. Therefore, there is a forcing approach to eliminate interference between based on equivalent baseband channel is considered. We have the equivalent baseband channel matrix in Formula 21. As mentioned above, it is a low-dimensional square matrix. We also here define the channel update period, TC. We also call it time slot, as the equivalent channel update. Then there's a forcing digital precoder of n+1 th channel update period is derived in Formula 22. In general, baseband channel should be updated at each time slot to maintain the spectrum efficiency. However, when the relative velocity is high, there is insufficient time for channel estimation. Fortunately, in terms of Formula 16, the channel of adjacent time slots are correlated, that the outdated equivalent CSI can be used to predict the digital precoder. Then we can obtain the Formula 23. The inverse of the sum of two arbitrary matrix is generally difficult to split. Fortunately, as epsilon is large, a noise matrix can be considered as a distribution sum. Turn to Newman series, it provides approximations of the inverse of sum of two matrices when one of the matrices have enters of small magnitude. Then, formula 23 can be rewritten as in formula 24. When epsilon is large enough, the first sum in 24 is reserved and the following terms are ignored. The predictive digital precoder can be approximately written in formula 25. Next, I will discuss hybrid precoding data transmission processing. The definition of beam update period and channel update period has been explored above, and it is assumed that one beam update period contains several channel update periods. The equivalent baseband channel almost unchanged within one channel update period, but could vary for different channel update periods. LA and LG nearly do not vary in one beam update period. They vary for different beam update periods. Then we can see that step 1 as the initial channel update period. Each mobile node sends its location to control center. Analog precoder and combiner are designed. Then in step 2, control center transmits pilot symbols to calculate baseband channel. On step 3, baseband channel is fed back to control center. Then digital precoder can be derived and data streams are transmitted to each mobile node. In step 4, as the second channel update period, analog precoder and combiner are unchanged. Digital precoder is predicted according to formula 25. Then the pilot symbols and data stream are sent simultaneously by hybrid precoding. The pilot symbols are used to estimate the baseband channel of current time slot. In step 5, the channel of current time slot is fed back to control center to predict the digital precoder of next time slot. Then we repeat step 4 to step 5 until the end of a beam update period. And at the last channel update period, all the data streams need to be transformed. The details are shown in figure 2. For second and subsequent beam update period, if a mobile node moves uniformly in a straight line, location information does not need to be fed back. The analog precoder can be obtained according to 17 and formula 20. Otherwise, the location should be fed back at the beginning of each beam update period. I'm going to show you the numerical results of the strategy. Here are the simulation parameters. In figure 3, we compare the conventional hybrid precoding and the proposed strategy. It illustrates that the spectrum efficiency of the system with different channel coherence time vary SNR. As shown in figure 3, the spectrum efficiency of the proposed strategy is close to the optimal hybrid precoding. As SNR goes large, a gap can be seen between the optimal strategy and the proposed strategy. In low SNR range, the noise is the main influence for performance, while for high SNR range, the interference between the data stream has a great impact on performance. Residual interference due to the approximation of Newman series cause performance degradation. It also shows that as channel coherence time becomes small, the proposed strategy approaches the optimal strategy closely. This is because the correlation between channels of adjacent time slots becomes Zhang, that the predicted precoder matrix has a smaller difference with optimal precoder matrix. Therefore, we have to make a trade-off between spectrum efficiency and channel coherence time in practice. It can also be seen that spectrum efficiency of conventional strategy is close to the proposed strategy. The reason is that we only consider the single time slot without consider the influence of the time on the performance. Figure 4 depicts the spectrum efficiency via time slot index with different hybrid precoding strategy under the assumption that SNR is 20 dB, coherence time is 0.1 ms. In simulation, 4 beam update periods are considered here, and each beam update period contains 5 channel update periods. It can be seen that the spectrum efficiency of the proposed strategy fluctuates under the optimal performance over time. In contrast, because of channel mismatch, the spectrum efficiency of coherence strategy continues to degrade as time goes on during one beam update period until it updates as an CSI. It's obvious that the proposed strategy can still maintain high spectrum efficiency in high mobility scenarios compared with the conventional strategy. Hence, therefore, the proposed strategy is applicable in high mobility scenarios. By the way of the conclusion, we have developed a novel hybrid precoding strategy for air-to-air systems to overcome the problem of CSI outdated in high mobility scenarios and huge path loss for long-distance transmission. For the further future work, we will study the air-to-ground high mobility communications. In this environment, there will be endless paths and there will be huge Doppler shifts, causing significant performance degradation. There are the reference and thanks to these authors for providing me with a lot of inspiration. Thank you for your attention.